In the previous lecture, we have introduced negative exponential distribution, and we gave its origin as the distribution of the waiting time for the first occurrence in a Poisson distribution. So, we considered probability of t greater than t. If t is having an exponential distribution, so if we consider probability of say t greater than a number a, then it is equal to e to the power minus lambda a. Now, if we consider, so this means that the first occurrence has not taken place till time a, that means in the interval 0 to a, it has not taken place. So, if we consider probability of say t greater than say a plus b, given that t is greater than b. So, if we consider this as in event a, this as event b, then it is equal to probability of a intersection b divided by probability of b. Now, a intersection b, so here a is a subset of b, therefore, this becomes probability of a divided by probability of b, that is probability of t greater than a plus b divided by probability of t greater than b. So, by the formula that we have developed, this one will become equal to e to the power minus lambda a plus b divided by e to the power minus lambda b. So, after simplification it becomes e to the power minus lambda a, which is nothing but the probability of t greater than a. So, this phenomenon represents that if the event has not taken place till time b, then it will not take place till an additional time a. The probability of that is same as that the event will take place after time a starting from time 0. That means, if we are considering the waiting time for a certain thing, then the probability of waiting for an additional time is same irrespective of the starting point. So, like geometric distribution, this is called the memoryless property of the exponential distribution. You can see that exponential distribution is analogous to the geometric distribution of the discrete case. In the geometric distribution, we were considering Bernoullian trials and we were waiting for the first success or first occurrence. So, here also it is a Poisson process and we are waiting for the first occurrence. So, in a sense this exponential distribution is a continuous analog of the geometric distribution. So, if we consider say occurrence to be say failure of certain component in a mechanical system, and if we know that the system has not failed till that time, then the probability of failure after a certain time is same irrespective of the starting point where we have taken. So, this type of thing is interesting because many times we buy say second hand item, second hand transistor, second hand computer or calculator, because if it is still working, then the probability of its failure after a certain time will remain the same. So, this is because of the memoryless property of the exponential distribution. Let us also consider some modifications of this exponential distribution, because here we are starting from the time 0, but many times for example, you consider certain item which we are purchasing from the market, then the market when you are purchasing, then the shopkeeper gives you a guarantee for certain time like 1 year or 2 year etc. That means, the item is not supposed to fail before that, because if it is failing he is taking it back. So, it is again as if you are starting afresh. So, this is considered as a shifted exponential distribution by certain constant. Another thing we notice here is that when we consider the form lambda e to the power minus lambda t, where lambda was the rate of the Poisson distribution, then the mean of this turns out to be 1 by lambda. And since there is a single parameter, if we write say 1 by lambda as say something like sigma, then this will become 1 by sigma e to the power minus t by sigma. So, in the popular form with the shifted origin, we can consider the form of exponential distribution as, so we call it shifted exponential distribution. The density we can write as 1 by sigma e to the power minus x minus mu by sigma. So, here x is greater than mu and of course, sigma is positive. An advantage of this form is that in place of time, if we are considering some other representation for x, x need not be time all the time. So, if it is something else, then mu can be negative also, and then also this distribution remains valid. So, you can consider this is a generalization of the original exponential distribution. If we consider this particular form, then you can see it is easier to calculate the moments of x minus mu or x minus mu by sigma. So, let us consider expectation of x minus mu to the power k, which is of course not necessarily the central moment, because we have not shown that mu is the mean. However, for convenience we are considering this. So, it is equal to x minus mu to the power k 1 by sigma e to the power minus x minus mu by sigma dx from mu to infinity. So, we may put x minus mu by sigma is equal to y, that is 1 by sigma dx is equal to dy. Then this is equal to 0 to infinity sigma to the power k y to the power k e to the power minus y dy, that is equal to gamma k plus 1 or k factorial sigma to the power k. So, in particular, if we consider expectation of x minus mu to the power 1, this is equal to sigma. This means mean of the shifted exponential distribution is mu plus sigma. If we had considered lambda there, then it would have been mu plus 1 by lambda. So, definitely we would be interested in the variance here. So, expectation of x minus mu square is equal to 2 sigma square, which gives us expectation of x square minus 2 mu expectation x plus mu square is equal to 2 sigma square. So, further simplification gives expectation of x square is equal to 2 sigma square minus mu square plus 2 mu expectation x is mu plus sigma. So, this becomes equal to 2 sigma square plus 2 mu sigma minus mu square plus 2 mu square. So, it becomes plus mu square. So, if we calculate the variance of x, that is equal to expectation x square minus expectation x whole square, that is equal to 2 sigma square plus 2 mu sigma plus mu square minus mu plus sigma whole square, which is simply sigma square. So, variance has not changed by shifting. This is true because the fact that variance is independent of the shift in the origin. The variance of x plus c is expectation of x plus c minus expectation of x plus c whole square. So, this is equal to expectation of x minus expectation x whole square, which is the variance of x. So, the variance is unaffected by the change in the origin. We can consider here the moment generating function of this and also the moment generating function of the original exponential distribution. So, let us look at this. Moment generating function at a point u, it is equal to expectation of e to the power u x. So, this is equal to 1 by sigma e to the power u x e to the power minus x minus mu by sigma dx mu to infinity. So, we can consider here x minus mu by sigma is equal to y, the transformation that we made here. So, it is becoming 0 to infinity e to the power u, and x becomes sigma y plus mu e to the power minus y dy. So, this can be simplified it is equal to e to the power mu u e to the power y sigma u minus 1 dy from 0 to infinity, e to the power mu u, and this becomes e to the power y sigma u minus 1 divided by sigma u minus 1, provided sigma u is less than 1 or u is less than 1 by sigma, which was basically lambda, from 0 to infinity. So, at infinity this becomes 0 because I am taking sigma u to be less than 1, and at 0 this becomes 1. So, you are getting e to the power mu u divided by sigma u minus 1. In particular, if we had taken mu is equal to 0, then this mx u would have been 1 by sigma u minus 1. If we put sigma is equal to say 1 by lambda, then this will become 1 by u by lambda minus 1, that is equal to lambda by u minus lambda. Where there is a minus sign here, because when we put 0 there is a minus sign here. So, this will become actually equal to e to the power mu u 1 minus sigma u. So, this will become with a minus sign 1 by 1 minus sigma u. So, minus is here. So, this is equal to lambda by lambda minus u for u less than lambda. So, the moment generating function of an exponential distribution, when we consider the original form, that is waiting time starting from the 0, then mgf is lambda by lambda minus mu or 1 by 1 minus sigma u. If we consider the starting from mu, then it is e to the power mu u by 1 minus sigma u. So, here we can see the relationship between these exponential distributions. So, let x follow exponential distribution with parameters mu and sigma. Consider the transformation y is equal to say a x plus b. Consider the moment generating function of this. Then it is expectation of e to the power u into a x plus b. This is equal to e to the power b u and the moment generating function of x at the point a u. So, what is the moment generating function of x at the point u? That we derived it as e to the power mu u by 1 minus sigma u for u less than 1 by sigma. So, if we make use of this term here, in place of u we can put a mu here. So, it is equal to e to the power a u mu divided by 1 minus sigma a u. So, this we can adjust and write it as a mu plus b u see this term was bu and here it is au mu. So, mu a mu, this actually u we will interchange here. So, it becomes a mu plus b and then u divided by 1 minus a sigma u. Compare this. The term here, the moment generating function of x is e to the power mu u by 1 minus sigma u. So, here mu is replaced by a mu plus b and sigma is replaced by a sigma. The form is the same. At the same time, since we have replaced a u by u in the expression for mx, this expression was valid for u sigma less than 1. So, here a u sigma must be less than 1. That means u is less than 1 by a sigma. So, obviously, you can see by comparing this that this is an MGF of, which is MGF of exponential distribution with parameter a mu plus b and a sigma. So, this means we have proved the following theorem: if x follows exponential mu sigma, then y is equal to a x plus b, where a is not 0, follows exponential distribution with parameter a mu plus b a sigma. This is basically linearity property of an exponential distribution. That means any linear function of an exponential distribution is again having exponential distribution. So, this form is more general. This is a 2 parameter exponential distribution and it is more useful. In particular, we will have, if x follows exponential say mu 1 by lambda, then x minus mu will follow exponential 1 by lambda. That means the standard form with the density lambda e to the power minus lambda t. So, both the forms are useful. Let us take one example here for exponential distribution. The time to failure in months. So, suppose it is x of the light bulbs produced at 2 manufacturing plants say A and B obeys exponential distribution with means 5 and 2 months respectively. Plant B produces 3 times as many bulbs as plant A. The bulbs are mixed, so they look indistinguishable to a naked eye, and sold. What is the probability that a randomly selected bulb will burn at least 5 months? So, let us consider here the distribution of x is exponential, but it is not the same for all the bulbs. For a certain proportion of bulbs, the distribution is exponential with mean 5. That means, the density will be 1 by 5 e to the power minus x by 5, and for certain bulbs the mean time is 2 months. So, the density will be 1 by 2 e to the power minus x by 2. So, if we are considering the x as the time or life of bulb, then x, given that it is produced by plant A, this has a density 1 by 5 e to the power minus x by 5 for x greater than 0, and of course 0 otherwise. If we are considering the bulb produced by plant B, then the density function is half e to the power minus x by 2 for x greater than 0. We are interested in a randomly selected bulb's life to be more than 5 months. So, here we can apply the theorem of total probability. So, probability of x greater than 5 given that it is produced by plant A into the probability of being produced at plant A plus probability of x greater than 5 given that it is produced at plant B into probability of plant B. So, this is equal to, now if we are considering probability of x greater than 5 from this one, then consider the general formula, probability of x greater than a is equal to e to the power minus a lambda. So, here lambda is equal to 1 by 5 and a is equal to 5. So, this becomes e to the power minus 5 into 1 by 5 into probability of A. Now, what is probability of A? It is given that B produces 3 times as many bulbs as A. So, the probability of the bulb being selected from A may be 1 by 4 and the probability of this may be 3 by 4. So, this is into 1 by 4 plus e to the power minus 5. Here the parameter is 1 by 2, 3 by 4. So, this can be simplified and it is 0.1534. So, probability that a randomly selected bulb is working beyond 5 months is only 0.15 approximately, which may look slightly surprising, because you say that there are 2 plants and from one of the plants it is 2 months and from another plant it is 5 months. So, it should be nearly half, but it is not so, because the plant B gives more supply compared to the plant A, and in the plant B the probability of having more than 5 months is much smaller, because it is e to the power minus 5 by 2 and here it is e to the power minus 1. So, this number is obviously larger than this number. Now, consider that we are not interested in a single occurrence or a single failure or a single happening in a Poisson process. In place of that, we are considering, so consider a Poisson process let us denote xt with rate lambda, and let xr denote the time, well in place of x we will use notation say tr because x is being used here. Let tr denote the time of rth occurrence. So, in place of the first occurrence we are looking at a certain number of occurrences, as we had discussed yesterday also, like in the negative binomial distribution, that a certain major event may occur as a consequence of certain smaller events. For example, if 1000 smaller intensity earthquakes occur, then it may make the earth to crumble and a major earthquake may occur. A sequence of certain mishaps may close down the plant itself. A sequence of, so any smaller kind of events may lead to a major disaster. So, we may be interested in the waiting time for that. Of course, considering the events to occur in a Poisson process. For example, a certain number of occurrences have occurred, say a certain number of people purchase certain tickets, then we may have to close down the window because the seats are full. So, what is the distribution of TER? Once again, we can consider probability of TER greater than T. So, starting from a time 0, consider time small t. If we say that rth occurrence has not taken place till this time, suppose this is the rth occurrence, that means in the interval 0 to t, less than or equal to r minus 1 occurrences will be there. So, this event is equivalent to probability of xt less than or equal to r minus 1. Of course, here t is positive. It is equal to 1 for t less than or equal to 0. Now, xt is having a Poisson distribution with parameter lambda t. So, this is equal to e to the power minus lambda t to the power j by j factorial summation j is equal to 0 to r minus 1. This is for t greater than 0 and it is 1 for t less than or equal to 0. Consequently, we can write down the cumulative distribution function of TR as f of TR at the point t, that is 1 minus probability of TR greater than t, and this is equal to 0 for t less than or equal to 0. It is 1 minus summation j is equal to 0 to r minus 1 e to the power minus lambda t to the power j by j factorial for t greater than 0. So, you can observe here it is a time variable and this is an absolutely continuous function. So, the probability density function can be obtained by differentiation of this . Now, for t less than or equal to 0 it is 0 and in this particular portion we are having sum of a series. So, we have to do term by term differentiation. So, this is equal to 0 for t less than or equal to 0 and in this portion now this is d by dt of e to the power minus lambda t plus lambda t into e to the power minus lambda t plus lambda t square e to the power minus lambda t by 2 factorial and so on plus e to the power minus lambda t to the power r minus 1 by r minus 1 factorial for t greater than 0. So, here you observe that when we differentiate, here one term is there, but thereafter each term is a product of two terms involving t. So, when we differentiate, we have to do by applying the formula of derivative of a product. So, if we expand the terms, the derivative of the first term will give us minus lambda e to the power minus lambda t and there is a minus sign here. Consequently, we will get it as lambda e to the power minus lambda t. If we look at the second term and we look at the derivative of this, we will get lambda multiplied by e to the power minus lambda t and there is a minus sign here. So, we will get here minus lambda e to the power minus lambda t and observe that this can cancel out. The next term will be the derivative of this. So, that will give minus lambda and minus is there. So, it becomes plus lambda square t e to the power minus lambda t. Now, look at the third term and derivative of this. So, if we look at the derivative of this one, here t square is coming. So, 2t and this 2 will cancel out and there will be a minus sign. So, we will get with a, because there was a minus sign outside, it becomes minus lambda square t to the power minus lambda t. So, you can easily observe that this is a telescopic sum. The final term will be plus, which will be contributed by this term, that will become lambda to the power r t to the power r minus 1 by r minus 1 factorial e to the power minus lambda t. So, this will be the left out term. So, we are getting the probability density function of T r as lambda to the power r t to the power r minus 1 e to the power minus lambda t by gamma r for t greater than 0. Here lambda is a positive parameter. In the derivation, we have considered r to be a integer because it is occurrence, but after writing down this, you can see that it is valid for r greater than 0, any positive real number. So, this is known as a gamma distribution or Erlang's distribution. So, this distribution arises as the distribution of the waiting time for the rth occurrence in a Poisson process in place of the first occurrence. If you put r is equal to 1, you will get the exponential distribution, because this term will vanish, you will get lambda e to the power minus lambda t. So, this is a generalization of the exponential distribution, but it has much more applicability because we are looking at a higher order of occurrences in a Poisson process. Apart from the regular applications, one can see the characteristics of this distribution. If we consider a kth order non-central moment, that is mu k prime. So, mu k prime is equal to integral from 0 to infinity t to the power k lambda to the power r t to the power r minus 1 by gamma r e to the power minus lambda t dt. So, obviously, this is a gamma function. You can write it as lambda to the power r by gamma r t to the power k plus r minus 1 e to the power minus lambda t dt. So, it is lambda to the power r by gamma k plus r divided by lambda to the power k plus r. This is equal to, that is mu k prime is equal to gamma k plus r of course, this is valid for any k greater than 0, but we will be more concerned with the positive integral moments. So, mu 1 prime is equal to gamma r plus 1 by gamma r 1 by lambda, that is r by lambda. So, if the waiting time for the first occurrence was average waiting time for the first occurrence was 1 by lambda, then for the rth occurrence it will be r by lambda. So, this is again because of the memoryless property of the exponential distribution, because after first occurrence we can again consider it as the starting of the process observing from time 0. So, again for the second occurrence waiting time will be 1 by lambda and so on. If we consider mu 2 prime, then this becomes r into r plus 1 by lambda square, and therefore, mu 2, that is the variance of this distribution, is equal to r into r plus 1 by lambda square minus r square by lambda square, that is r by lambda square, which is again you can see in the exponential distribution the variance was 1 by lambda square, and if we are looking at the variance of the rth occurrence, then it becomes r by lambda square. Let us look at one application of this. the CPU time requirement T for jobs has a gamma distribution with mean 40 and standard deviation 20. This measure is in seconds. Any job taking less than 20 seconds is a short job. What is the probability that of 5 randomly selected jobs, at least 2 are short jobs? So, in order to answer this question, let us consider the setup. Here mean is given to be 40, so that is r by lambda is 40, and standard deviation. So, here variance is r by lambda square. So, r by lambda square is 400. So, this is a 2 parameter distribution, and we have now 2 equations. So, we can have r by lambda is equal to 40, r by lambda square is equal to 400. So, if we solve this, we get r is equal to 4 and so lambda is equal to 1 by 10. So, that is right. What is the probability of a short job? That means t is less than 20. So, we need to consider the density function of t here. F t is equal to e to the power minus lambda t. So, that is t by 100, t to the power r minus 1, that is 3, then lambda to the power r, that is 1 by 10 to the power 4, and gamma r. This is for t greater than 0. So, we need to calculate 0 to 20 the integral of this density, 1 by gamma 4, 10 to the power 4, e to the power minus t by 10 t cube dt. This is the probability of a randomly selected job to be a short job. So, if we want to evaluate this, we can consider, since exponential function is involved, the integral will be at one end something value 1 and at another point some value will be there. So, it is convenient if we consider this as 1 minus 20 to infinity 1 by 6 into 10 to the power 4 e to the power minus t by 10 t cube dt. So, from the integrals integrand we can observe that it is convenient if we put t by 10 is equal to y, that is 1 by 10 dt is equal to dy. So, this becomes equal to 1 minus, this will be 2 to infinity 1 by 6 e to the power minus y, y cube dy. So, this is not a complete gamma function, this is an incomplete gamma function because the integral is from 2 to infinity. So, we can do integration by parts, and after doing certain simplification, this one will turn out to be 1 minus 19 by 3 e to the power minus 2, which is approximately 0.1429. So, probability of a randomly selected job being a short job is only 0.1429. That means, in the gamma distribution, if the mean is 40 and the standard deviation is 20, the probability of job being over in mu minus sigma is actually much smaller. Now, we can consider the random variable, say Z is the number of short jobs out of 5. Then Z is following binomial distribution with n is equal to 5 and p is equal to 0.1429. This is p, this is n. We are saying what is the probability that at least 2 jobs are short jobs. That means probability of Z greater than or equal to 2. This we can consider as probability Z is equal to 0 and Z is equal to 1. You subtract from 1, that is a complementary event. So, this is equal to 0.1 minus 0.1429 to the power 5 minus 5c1, 1 minus 0.1429 to the power 4 into 0.1429. So, this can be evaluated and it is approximately 0.1519. So, the probability that at least 2 out of the 5 jobs are short jobs is quite small. This is because the probability of a single job itself being short job is much smaller. So, we may look at the moment generating function etc. of this distribution. So, moment generating function of the gamma distribution, expectation of e to the power u t r, that is equal to integral e to the power u t lambda to the power r by gamma r e to the power minus lambda t t to the power r minus 1 dt 0 to infinity. So, here if you see, this term can be combined with this. So, it becomes directly a gamma function. So, this is equal to lambda to the power r by gamma r e to the power minus t lambda minus u t to the power r minus 1 0 to infinity. So, this is just the gamma function lambda by lambda minus u to the power r and gamma r will be cancelling out. So, this is valid for u less than lambda. You can see the similarity from the moment generating function of the exponential distribution where r was 1. So, it was lambda by lambda minus u. So, we will show some relationship between the gamma distribution and the exponential distribution later on. The moments of the gamma distribution, as we have seen, can all be calculated from the general expression for mu k prime. So, mu 3 prime, mu 4 prime can be calculated and then mu 3 and mu 4 can also be calculated. You can see that it will be actually positive. So, all the gamma distributions will be in fact positively skewed. The reason is that if you look at the density function, it is lambda to the power r t to the power r minus 1 e to the power minus lambda t divided by of course gamma r. So, in the beginning if you consider at t is equal to 0 apart from r is equal to 1, this value is going to be 0, and if you are considering then t becoming larger, then in the beginning since it is t to the power r minus 1 it may increase little bit, but thereafter this term will dominate and therefore, the densities will always be positively skewed for various gamma distributions. Of course, it will depend upon what is the value of r and what is the value of lambda for different shapes, but whatever be the shapes they will be positively skewed. the peak will of course depend upon the value of the r and lambda. If we are considering the exponential distribution or the gamma distribution as the life of certain components, then another interesting distribution in the same direction is the so called Weibull distribution. The general form of a probability density function of a Weibull distribution is given by alpha beta x to the power beta minus 1 e to the power minus alpha x to the power beta, where x is always positive and alpha and beta are positive parameters. So, quite naturally one can see the form of the CDF here, because if you integrate from since x is positive valued random variable, the integral will be from 0 to x f t dt for x positive, and it is 0 of course for x less than or equal to 0. So, if you consider this integrand, it looks like a derivative of e to the power minus alpha x to the power beta, and therefore, when we calculate the CDF, this will be simply equal to 1 minus e to the power minus alpha x to the power beta for x positive, and it is 0 for x less than or equal to 0. If we put beta is equal to 1, then this term vanishes, this term becomes e to the power minus alpha x. So, you get alpha e to the power minus alpha x. So, that becomes exactly the density of an exponential distribution. So, this Weibull distribution is actually a generalization or extension of the exponential distribution. So, we will see that what is the significance of making power x to the power beta here, because in the exponential we had alpha e to the power minus alpha x. So, x has been replaced by x to the power beta. So, first is that we can look at its moment structure. So, obviously, you can make use of the gamma functions. If I consider expectation of x to the power k, it is alpha beta x to the power beta plus k minus 1. So, quite obviously, you can understand here that if we put x to the power beta is equal to y, that is beta x to the power beta minus 1 is equal to dx is equal to dy, then this becomes integral from 0 to infinity alpha and x to the power beta minus 1 term is combined here. So, you have x to the power k, that is y to the power k by beta e to the power minus alpha y dy. So, this is simply a gamma function, and the expression for this turns out to be alpha gamma k by beta plus 1 divided by alpha to the power k by beta plus 1. That means, gamma k by, or you can write it as k plus beta by beta divided by alpha to the power k by beta. So, in particular, if I am looking at the mean, so mu 1 prime is equal to expectation of x, that is equal to alpha 1 by beta plus 1 gamma of this divided by alpha to the power 1 by beta plus 1, that is equal to alpha to the power minus 1 by beta gamma of beta plus 1 by beta, and mu 2 prime will become alpha to the power minus 2 by beta gamma of beta plus 2 by beta, and therefore, the variance of the Weibull distribution will be alpha to the power minus 2 by beta gamma beta plus 2 by beta minus gamma beta plus 1 by beta whole square, which looks slightly complicated, but nevertheless the functions of the gamma functions can be easily calculated using tables of the gamma distribution or the from calculators or computers. Nowadays this can be easily. However, this distribution has more importance in the reliability analysis of certain mechanical or electronic systems. So, let us define what do you mean by the reliability of a system. So, if T denotes the survival time or the life of a system, so we can consider probability of T greater than T. This means the system has been functioning till time T, or it has not failed till time T, or the system is working at time T. The probability of system working at time T is called the reliability of the system at time T. Reliability of the system at time T. So, using this we can define another quantity, and of course, you can easily see that this is equal to 1 minus the CDF at the point T. We also define what is known as instantaneous failure rate of system at time T. So, let us consider the interpretation of this. The system is functioning at time T, and immediately after the time T it fails. That means in an interval from T to T plus H. So, if we are considering the rate, we consider it divided by H and take limit as H tends to 0. Let us give some notation, say H of T. We also call it hazard rate at time T. So, this we define for any random variable which is denoting the life of a system. So, we call failure rate at time T or hazard rate at time T. That means, given that the system is functioning at time T, what is the probability that it will fail immediately after that, and therefore, if we want to calculate the rate, then we divide by the length of the interval and take the limit as this. So, let us evaluate this. Now, if we consider this as event A and this as event B, then this is probability of A intersection B divided by probability of B. Now, once again you can see that A is a subset of B. So, this becomes probability of T less than capital T less than or equal to T plus H divided by probability T greater than T, H limit as H tends to 0. So, this term, if you see, it is nothing but the density function of the variable T, because we are taking limit as H tends to 0. See, you can expand it like this. The numerator becomes f of T plus H minus f of T by H, and this is RT. So, this term is nothing but the Ft by RT, or you can consider it as Ft divided by 1 minus Ft. So, the hazard rate of a lifetime distribution can be denoted by the density divided by the reliability, or the density divided by 1 minus the cumulative distribution function of the random variable. So, we are calling it as Ht. We can notice another relationship here. This is minus d by dt log of 1 minus Ft. So, So, this looks like a first order differential equation. We can integrate it out and we will get log of 1 minus f t is equal to and therefore plus of course a constant of integration. So, 1 minus f t becomes some k times e to the power minus integral h t dt. This shows that given the distribution one can calculate the hazard rate, given the hazard rate function one can determine the CDF and hence the probability density function of the random variable. We will look at these quantities, that is the reliability, the hazard rate in context of the Weibull distribution, the exponential distribution, and try to see what does it signify. So, in the next lecture we will be covering these issues. Thank you.